The object is small, compact, painted a dull, industrial orange that has nothing to do with visibility and everything to do with survival. It is not elegant. It is not aerodynamic. And yet, it is the most trusted witness in aviation history. Before a single line of code is written, before a single rivet is driven into aluminum skin, the modern aircraft is designed around an assumption that no matter how catastrophic the failure, this device will endure. This confidence did not appear by accident. It was engineered. In the early decades of flight, aviation was built on optimism and intuition. Airframes were fabric and wood, engines were unreliable, and accidents were accepted as the cost of progress. When an aircraft fell from the sky, the investigation relied on eyewitnesses, on fragments scattered across fields, and on the often fallible testimony of survivors. Engineers believed they understood their machines. They trusted their calculations, their safety margins, their materials. The architecture of confidence rested entirely on human certainty. That certainty shattered with speed. As aircraft grew larger and faster, so did the consequences of failure. The introduction of pressurized cabins in the jet age transformed the fuselage into a pressure vessel, cyclically inflated and deflated with every climb and descent. The aircraft's skin was no longer just a fairing. It became a structural component, holding back a differential pressure equivalent to thousands of kilograms of force. Engineers believed aluminum alloys, carefully riveted and reinforced, were invincible. They were wrong. The first invisible enemy was fatigue, not dramatic overload, not a storm or a collision, but repetition, stress applied again and again, always below the theoretical limit, quietly altering the crystalline structure of metal. Each pressurization cycle introduced microscopic slip-ins. Each landing added another increment of strain. The aircraft appeared unchanged, but deep within the lattice of aluminum, cracks were being born. The industry did not yet have a language to describe this process, nor did it have tools to measure it. When early jetliners began to fail catastrophically, tearing apart at altitude without warning, the confidence of engineers collapsed overnight. Investigators recovered fragments of fuselage that looked as if they had been ripped open by explosives. In reality, the culprit was geometry. Sharp corners and window cutouts created stress concentrations far higher than predicted. At those points, fatigue cracks initiated and propagated invisibly, cycle after cycle, until the remaining material could no longer carry the load. The aircraft did not fail gradually. It failed instantly. The realization was brutal. Modern machines could die silently, leaving no survivors, no witnesses, and no clear explanation. Aviation faced a fundamental problem. Without a reliable way to understand what happened in the final moments, every new aircraft design was built partly in the dark. The solution would not come from aerodynamics or propulsion. It would come from metallurgy, thermodynamics, and the physics of destruction. Engineers proposed a radical idea, a device that would experience the same environment as the aircraft, survive forces that would obliterate the structure around it, and record the truth without interpretation. It would not rely on human memory or speculation. It would be objective, mechanical, absolute. The concept of the crash-survivable recorder was born. Early designs were crude. Magnetic wire recorders adapted from industrial equipment, housed in steel casings with little understanding of impact dynamics or post-crash fires. They failed often. Heat erased data. Deceleration snapped spools. Water intrusion destroyed evidence. Each failure revealed a new flaw, forcing engineers to confront physical realities they had underestimated. Impact was not a single force. It was a sequence. Initial deceleration spikes exceeding thousands of G, followed by secondary impacts, tumbling, crushing loads, and often prolonged exposure to fire at temperatures exceeding 1,000 degrees Celsius. The recorder had to survive all of it. Material science became the battlefield. Steel was strong, but too heavy. Aluminum was light, but melted too easily. Engineers turned to titanium alloys, not for their strength alone, but for their unique combination of high melting point, fracture toughness, and resistance to creep under extreme thermal stress. Layers were added, not randomly, but strategically, an outer sacrificial shell to absorb energy, inner insulation to delay heat transfer, and a core capsule to protect the memory unit. Inside, data storage evolved. Magnetic tape gave way to solid-state memory, eliminating moving parts that could shatter under acceleration. Memory boards were potted in shock-absorbing compounds designed to deform plastically, dissipating energy without transmitting peak loads to delicate electronics. The recorder was no longer a passive box. It was a carefully engineered system, designed to fail in controlled ways so that its heart would not fail at all. As confidence in the recorder grew, so did reliance on it. Investigators began to trust recorded data more than eyewitness testimony. Flight parameters revealed truths pilots never had time to speak. Control inputs, system failures, warning tones, cockpit conversations, all captured without emotion. But this reliance introduced a new form of engineering hubris. Designers began to assume that because the recorder existed, it would always tell the full story. That assumption ignored a critical fact. The recorder only survives if its protective architecture performs exactly as intended. And that architecture, like the aircraft itself, is subject to fatigue, manufacturing defects, and design compromise. Every crash became not only a test of the aircraft, but a test of the recorder. Some failures were subtle. A fire that lasted minutes longer than certification standards anticipated. A deep ocean impact that crushed housings beyond their elastic limit. A battery that depleted before rescue teams arrived. Each scenario exposed margins that had been assumed sufficient, but were not. The investigation process became increasingly forensic. Metallurgists examined fracture surfaces under electron microscopes, identifying brittle versus ductile failure modes. Thermal analysts reconstructed heat flux profiles through insulation layers. Engineers compared recorded deceleration data with finite element models of the recorder housing, searching for discrepancies. In several cases, recorders were recovered intact, but silent. Data unrecoverable. The box had survived physically, but not functionally. These failures forced a reckoning. Certification standards were rewritten. Impact requirements increased. Fire exposure times doubled. Submersion depths extended to thousands of meters, acknowledging the reality of oceanic flight paths. Locator beacons were redesigned for longer battery life and stronger acoustic output, recognizing the challenge of deep water recovery. The black box became heavier, stronger, and paradoxically, more vulnerable to the very assumptions that justified its existence. Because as aircraft systems grew more complex, so did the data streams. Hundreds of parameters, thousands of samples per second. Software replaced hardware logic. Errors were no longer purely mechanical. They were algorithmic. The recorder faithfully captured data, but interpretation became the new challenge. Engineers now faced not a lack of information, but an overwhelming abundance of it. And yet, the fundamental truth remained unchanged. Every modern aircraft is still a collection of materials pushed to their limits. Aluminum, titanium, composites, all subject to fatigue, delamination, corrosion, and manufacturing variability. The recorder does not prevent failure. It documents it. In this way, the black box is both a triumph and a confession. It acknowledges that no matter how advanced the design, no matter how rigorous the certification, failure is always possible. And when it happens, understanding it is not optional. It is an obligation. The history of the crash recorder is therefore inseparable from the history of structural failure. Each improvement was written in response to a disaster. Each layer of insulation added after a fire proved longer than expected. Each increase in impact tolerance followed a crash that exceeded prior assumptions. The device exists because engineering confidence, left unchecked, repeatedly proved insufficient. As aircraft continue to evolve, incorporating carbon fiber composites and fly-by-wire systems, the recorder evolves with them. New challenges emerge. How composite structures fail differently than metals. How data integrity is preserved under electromagnetic interference. How future autonomous systems will record decision-making logic. The black box remains silent, waiting. Because when the next microscopic crack begins to grow, when stress redistributes itself invisibly through a structure designed to be perfect, when physics asserts itself without warning, it will be there. Recording, enduring, preserving the truth long after the aircraft has ceased to exist. And that truth, written not in words but in data, will once again expose the limits of human certainty. The confidence placed in the crash recorder hardened into doctrine during the decades that followed. It became an assumption embedded in certification philosophy itself. If something went wrong, the data would explain it. But this belief masked a deeper problem. Engineers were still learning how things failed, and they were learning it backward, from wreckage to theory. The recorder was never designed to prevent catastrophe. It was designed to survive it. That distinction matters. As jetliners entered routine service, flight cycles accumulated faster than anyone had anticipated. Aircraft designed for a few thousand pressurization cycles were suddenly approaching tens of thousands. The fuselage behaved less like a static structure and more like a living organism, expanding and contracting, redistributing stress with every climb. Rivet holes elongated microscopically, lap joints fretted, protective coatings cracked. Moisture entered places it was never supposed to reach. Inside the metal, fatigue cracks grew not in straight lines, but in jagged, branching paths dictated by grain orientation and residual stress from manufacturing. Engineers had calculated average stresses. The metal responded to local ones. The recorder, bolted into the aft fuselage, experienced these same cycles. Its mounting brackets flexed, its fasteners loosened by imperceptible degrees. Thermal gradients developed as the aircraft climbed from hot runways into sub-zero stratospheric air. Expansion and contraction did not only affect wings and skins, they affected the box itself. This reality was not fully appreciated until recorders began to fail not during crashes, but during normal service. Data dropouts, corrupted tapes, electrical noise. The assumption that the recorder was a passive observer collapsed. It was a participant in the flight environment, subject to vibration spectra dominated by engines, airflow, and structural resonance. Engineers had underestimated vibration fatigue. Early mounting systems treated the recorder as a rigid mass. In reality, rigid masses amplify vibration. The solution required a shift in thinking, isolation, not rigidity. Elastomeric mounts were introduced, tuned to specific frequency bands. Too soft, and the recorder would experience large displacements during impact. Too stiff, and vibration energy would transmit directly into the housing. The margin between survivability and degradation was narrow. At the same time, memory technology evolved under pressure. Magnetic tape was sensitive to heat and shock, but solid-state memory introduced its own vulnerabilities. Solder joints cracked under cyclic strain. Silicon chips failed due to thermal cycling and radiation exposure at altitude. Engineers had traded one set of problems for another. The recorder became a microcosm of the aircraft itself, a complex system where no component could be evaluated in isolation. Then came fire. Post-crash fire was not a uniform phenomenon. It was chaotic, fueled by ruptured tanks, oxygen systems, and cabin materials. Flames impinged unevenly. Temperatures fluctuated violently. Some areas experienced brief but extreme heat spikes. Others endured lower temperatures for extended periods. Certification tests, however, were linear and controlled. A fixed temperature, a fixed duration. Reality did not follow the test script. Recovered recorders often showed partial charring, warped housings, and insulation layers that had performed exactly as designed, until they did not. Heat transfer is unforgiving. Once insulation saturates, temperature rises exponentially. Engineers learned that delaying heat was not enough. It had to be delayed long enough. This led to multi-layer thermal protection systems, ceramic fibers, phase change materials, and intumescent coatings that expanded under heat, increasing insulation thickness dynamically. Each layer introduced new failure modes. Ceramics cracked under shock. Phase change materials leaked. Coatings degraded over time. The box was becoming more resilient, but also more complex. Meanwhile, accident investigation itself was evolving. No longer content with surface explanations, investigators adopted forensic methodologies borrowed from metallurgy and fracture mechanics. Fracture surfaces were examined for beach marks, revealing the incremental growth of fatigue cracks. Chemical analysis detected corrosion products that had weakened structures years before failure. Finite element models reconstructed stress fields that had never been measured in flight. The recorder's data provided timing. Physics provided causality. In several landmark investigations, The recorder revealed a chilling pattern. Warnings ignored, systems misunderstood, human operators trusting machines that were already beyond their safe operating envelope. This exposed another layer of engineering arrogance, the belief that human factors were secondary to structural integrity. They were not. Cockpit voice recordings captured confusion, misinterpretation, and silence where action should have been. The recorder became not just a witness to mechanical failure, but to cognitive overload. Its presence forced the industry to confront uncomfortable truths about training, interface design, and the limits of human performance under stress. As a result, new parameters were added. More microphones, more sensors, redundant power supplies to ensure recording continued even as systems failed. The recorder was expected to operate until the final moment, even as the aircraft tore itself apart. That expectation drove another leap in material science. Housings were redesigned with crushable zones, inspired by automotive crash structures. Instead of resisting deformation entirely, the outer shell would collapse in a controlled manner, absorbing energy and protecting the core. This required precise control of alloy composition and heat treatment. Too brittle, and it would shatter. Too ductile, and it would transmit force inward. The metallurgy had to be exact. Testing grew brutal. Drop tests from heights simulating terminal velocity impacts. Penetration tests with steel rods representing wing spars. Fire tests exceeding fuel-fed flame temperatures. Deep-sea pressure chambers replicating ocean depths far beyond commercial flight routes. Each test failure rewrote assumptions. Yet despite this rigor, the recorder remained reactive. It explained disasters after they occurred. Engineers began to ask a dangerous question. If we understand failures so well now, why does it keep happening? The answer lay in complexity. Modern aircraft were no longer dominated by single-point failures. They failed through cascades. A sensor drifted out of calibration. Software interpreted data incorrectly. Control laws responded precisely, but to the wrong input. Structures were stressed in ways never anticipated during certification. The recorder captured the cascade, but only in hindsight. This realization sparked debates about real-time data transmission. If critical parameters could be streamed continuously, perhaps disasters could be understood or even prevented before impact. But this introduced new vulnerabilities, bandwidth limits, cybersecurity risks, and the sheer volume of data generated by modern aircraft. Engineers were once again at risk of believing technology could eliminate uncertainty. The black box remained the last line of truth, but it was no longer alone. It existed within a growing ecosystem of sensors, analytics, and predictive maintenance systems. Ironically, as the industry gained more foresight, the recorder's role became more symbolic, yet no less essential. Because prediction is never perfect. Materials still age. Fatigue still accumulates. Manufacturing variability still introduces microscopic flaws that no inspection can fully eliminate. The physics of crack propagation remains indifferent to human confidence. When failure comes, it comes fast. And in that moment, the recorder does exactly what it was designed to do. It survives. It remembers. It tells the story the machine could not tell itself. Not to assign blame, but to expose reality. The evolution of the black box is therefore not a story of technological triumph alone. It is a chronicle of humility forced upon an industry that repeatedly underestimated nature. Each improvement was earned through loss. Each layer of protection justified by wreckage. The recorder does not symbolize control. It symbolizes accountability. Because in aviation, understanding failure is the only path to preventing the next one. As aircraft entered the digital age, the black box crossed an invisible threshold. It was no longer a hardened notebook. It became a sensor fusion device, a silent mirror of the aircraft's nervous system. And with that transformation came a new kind of vulnerability, one not rooted in torn metal or melting insulation, but in logic. The early recorders documented speed, altitude, heading, and control surface positions. These parameters were physical, continuous, and intuitive. A control cable moved, a potentiometer changed resistance, and the recorder captured it. But modern aircraft replaced cables with electrons. Fly-by-wire systems translated pilot inputs into electrical signals, filtered through layers of software, laws, and protections before reaching an actuator. The recorder now had to document not just what moved, but why it moved. This required exponential growth in data. Hundreds of parameters became thousands. Sampling rates increased. Redundancy multiplied. And with each addition, the recorder's internal architecture became more complex, more densely packed, and more sensitive to the very forces it was meant to endure. Thermal cycling reemerged as a silent adversary. At cruising altitude, temperatures outside the fuselage fall below -50 degrees Celsius. Inside the recorder, internal electronics generate heat. The result is a thermal gradient across millimeters of material. Over time, this gradient induces differential expansion between circuit boards, solder joints, and protective encapsulants. Microscopic voids form in solder. Copper traces develop stress risers at sharp corners. Insulation materials stiffen and lose damping capability. Nothing fails immediately. Instead, degradation accumulates quietly, flight after flight, cycle after cycle. Exactly like the aircraft structure it observes. This symmetry is not poetic. It is dangerous. Several investigations uncovered recorders that had technically survived impact and fire, but whose data was corrupted long before the accident occurred. A memory sector damaged months earlier by vibration fatigue. A power conditioning circuit weakened by thermal stress. The recorder was present, intact, and partially blind. The industry responded by applying the same forensic rigor to recorders that it applied to airframes. Accelerated life testing became standard. Recorders were subjected to millions of vibration cycles at multiple frequencies, replicating years of service in weeks. Thermal shock tests forced electronics through extreme temperature swings far beyond operational limits. The goal was not just survival, it was integrity. Yet integrity itself became harder to define. Digital data does not crack like metal. It degrades through bit errors, timing faults, and synchronization loss. Engineers had to develop new methods to detect silent data corruption, implementing checksums, error-correcting codes, and redundant storage paths. The recorder began recording itself, monitoring its own health while monitoring the aircraft. This self-awareness came at a cost. More circuitry meant more failure modes. More software meant more assumptions. And assumptions are where hubris thrives. One assumption proved particularly dangerous, that the recorder would always be retrievable. Deep ocean accidents shattered this belief. Aircraft vanished into waters thousands of meters deep, beyond the reach of conventional recovery. Locator beacons transmitted acoustic signals, but batteries expired. Signals attenuated. Search areas expanded to hundreds of square kilometers. Months passed, sometimes years. In several cases, the recorder was never found. This forced a strategic reassessment. Engineers realized that survivability was meaningless without recoverability. A box that endures but cannot be located fails its mission just as completely as one destroyed on impact. New beacon designs emerged with extended battery life and stronger acoustic output. Some proposals included deployable recorders, devices that would eject from the aircraft during catastrophic failure and float, transmitting their position via satellite. The concept was elegant. It was also fraught with risk. Ejection mechanisms introduced their own failure modes. False deployment, failure to deploy, structural interference. And once again, engineers faced the same dilemma: complexity versus reliability. The debate exposed a deeper truth about aviation safety. No single device, no matter how advanced, can compensate for flawed assumptions upstream. The recorder can illuminate failure, but it cannot absolve design decisions that ignored fundamental physics. This became evident in accidents where recorders revealed not structural collapse, but systemic misunderstanding. Aircraft behaved exactly as designed. The problem was that the design itself assumed conditions that did not exist. Sensors iced over. Data became unreliable. Control systems responded correctly to incorrect information. Pilots trusted automation that had silently disengaged protections. The recorder captured it all with brutal clarity. In these moments, the black box exposed a new form of engineering arrogance, the belief that complexity equals safety. As systems grew more layered, responsibility diffused. Designers focused on subsystems. Software engineers optimized code. Certification authorities validated compliance. Few examined the emergent behavior of the whole machine under abnormal conditions. The recorder did. It showed how small deviations cascaded, how delays measured in milliseconds altered control logic, how redundant systems failed in correlated ways, how human operators, overwhelmed by contradictory cues, reverted to instinct. The forensic process became less about identifying a broken part and more about reconstructing a timeline of interactions. Data analysts synchronized hundreds of parameters, aligning them with cockpit audio, radar tracks, and wreckage distribution. Accidents were no longer singular events. They were sequences. This demanded a new kind of investigator, one fluent in materials science, aerodynamics, software logic, and human factors simultaneously. The recorder became the centerpiece of this synthesis. But even as its value increased, its limitations became more apparent. Sampling rates, though high, were finite. Parameters, though numerous, were still selective. Decisions made inside proprietary software often left no direct trace, only indirect consequences. Engineers faced an uncomfortable question. Was the recorder telling the whole truth, or only the part it was designed to see? This question drove further expansion. New parameters, higher resolution, more comprehensive logging. Yet each addition increased power consumption, heat generation, and internal stress. The recorder was approaching the limits of miniaturization and survivability. Materials science again became decisive. Advanced ceramics replaced older insulation materials, offering higher temperature resistance with lower mass. Composite housings combined metallic strength with energy-absorbing fiber layers. New potting compounds were engineered to remain viscoelastic across extreme temperature ranges, maintaining shock absorption without becoming brittle. Every material choice was a compromise: strength versus weight, insulation versus volume, durability versus inspectability, and every compromise carried risk. Despite this, the recorder continued to evolve because the alternative was unacceptable. Without it, accidents would regress into speculation. With it, even the most violent failures could be transformed into knowledge. The black box did not prevent tragedy. It converted tragedy into data. That conversion changed aviation permanently. Certification standards grew more conservative. Fatigue testing became mandatory for entire airframes, not just components. Full-scale fuselages were cycled until failure, revealing crack interaction effects never predicted by theory. Software validation protocols expanded, acknowledging that logic errors could be just as lethal as structural ones. These changes were not abstract. They were written directly from recorder data. In this sense, the black box is not merely a witness to failure. It is an active participant in the evolution of safety. Each byte of recovered data reshapes design philosophy, training doctrine, and regulatory oversight. Yet it remains, fundamentally, a reactive device. It waits. It waits as aircraft age, as microscopic flaws propagate invisibly through metal and composite alike. It waits as systems grow more autonomous, as human oversight shifts from direct control to supervisory monitoring. It waits as engineers push boundaries once again, confident in new materials, new algorithms, new assumptions. And history suggests those assumptions will one day be tested. When they are, the recorder will not intervene. It will not warn. It will not correct. It will endure. And in enduring, it will preserve the only thing that matters after confidence collapses: the truth of what actually happened. The moment of failure is never cinematic in the way fiction imagines it. There is no single loud crack that announces catastrophe. There is no dramatic pause. Physics does not hesitate. Failure arrives as a redistribution of load. In the final seconds before destruction, structures behave exactly as designed, until they are forced to do more than they were ever meant to do. A fatigue crack that has grown for years reaches a critical length. Stress intensity exceeds fracture toughness. The remaining material can no longer arrest propagation. At that instant, the rules change. Crack growth accelerates from millimeters per cycle to meters per second. The fuselage skin, once a continuous pressure boundary, ruptures explosively. Cabin air expands outward at near sonic velocity, tearing insulation, flooring, and wiring from their mouths. The pressure differential does not dissipate gently, it equalizes violently. Structural frames experience asymmetric loading. Loads shift faster than control systems can react. The aircraft does not break. It is unzipped by physics. Wings flex beyond their elastic limit as lift becomes unbalanced. Control surfaces saturate, commanded by systems still obeying logic that no longer applies. Engines ingest debris or flame out as airflow becomes chaotic. In some cases, the sequence unfolds in less than 2 seconds from initial rupture to total loss of structural integrity. Inside the cockpit, alarms overlap. Warnings designed to be sequential become simultaneous. Human cognition, optimized for linear information, collapses under nonlinear reality. And throughout this sequence, the recorder continues to function. Its accelerometers register spikes that exceed anything seen in normal service. Its microphones capture the sound of airflow where silence once existed. Data buses flood with fault messages as systems drop offline. Power fluctuates. Backup supplies engage. Recording does not stop. This is not accidental. It is the culmination of decades of engineering decisions made in response to past failures. The recorder's housing experiences the same deceleration as the aircraft, but its internal mass is decoupled by layers of engineered compliance. Shock waves propagate through the shell, reflect, and dissipate. Where the aircraft structure fractures, the recorder deforms plastically, sacrificing shape to preserve function. If fire follows impact, thermal protection begins its work. Outer layers char and ablate. Heat moves inward slowly, resisted by insulation designed to buy time measured in minutes. Electronics inside continue operating long enough to capture final parameters, even as the external environment becomes unsurvivable. Eventually, power is lost. Recording ceases. The recorder enters its final state, silent, inert, and intact. What follows is not an end, but a transition. Recovery operations begin amid uncertainty and debris. Investigators do not search randomly. They model descent trajectories, breakup patterns, ocean currents, and impact dynamics. The recorder's location is inferred, not guessed. When locator beacons function as intended, acoustic signals guide recovery teams through darkness and depth. When they do not, the search becomes a race against time and probability. Once recovered, the recorder enters a second phase of scrutiny. Physical condition is assessed first. Investigators examine deformation patterns, soot deposition, and thermal discoloration. These details provide context before any data is extracted. They tell a story even before memory is accessed. Data recovery itself is a forensic act. Memory modules are removed in cleanroom environments. Damaged connectors are bypassed. Custom interfaces are built to communicate with storage devices never meant to be removed. In extreme cases, individual memory chips are desoldered and read directly, bypassing failed circuitry. Every bit matters. The data is reconstructed, validated, and synchronized. Timestamps are aligned. Parameters are mapped. Audio is cleaned and filtered. What emerges is not a narrative, but a timeline, a precise sequence of states and transitions that describe how a system moved from normal operation to failure. This timeline often contradicts initial assumptions. Structural failure that appeared sudden reveals years of degradation. Pilot error suspected by public opinion reveals design ambiguity. Whether blamed in headlines proves incidental. The recorder does not care about perception. It records reality. This is where the true impact of the black box is realized. The investigation does not stop at identifying what failed. It seeks why it was allowed to fail. Certification assumptions are revisited. Design margins are questioned. Test methodologies are scrutinized. If a crack grew undetected, inspection protocols are reevaluated. If a system behaved unexpectedly, logic is rewritten. If humans misunderstood warnings, interfaces are redesigned. The recorder's data becomes evidence, not against individuals, but against flawed assumptions. Entire fleets may be grounded. Production lines halted. Airlines forced to modify procedures. Training syllabi rewritten. None of this is speculative. It is anchored in recorded fact. This process exposes the most uncomfortable truth in aviation engineering. Disasters rarely result from unknown physics. They result from known physics insufficiently respected. Fatigue was understood. Stress concentration was understood. Human limitations were understood. What failed was integration, the ability to account for how these factors interact over time. The recorder exists because integration is hard. As investigations conclude, recommendations are issued. Some are technical, others are operational. A few are philosophical. They challenge the culture that allowed confidence to override caution. These recommendations feed back into design offices, simulation labs, and regulatory frameworks. They alter the trajectory of aviation development in ways invisible to passengers but fundamental to safety. The aircraft that fly tomorrow are not safer by accident. They are safer because failures were recorded, analyzed, and acknowledged. And at the center of this process remains the black box, unchanged in purpose despite endless evolution in form. It does not innovate. It does not optimize. It does not predict. It endures. As new materials enter service, carbon fiber composites with failure modes unlike metal, bonded structures that hide damage beneath intact surfaces, the recorder adapts. New parameters are logged. New test standards emerge. The cycle repeats. Confidence builds. Boundaries are pushed. Margins are trimmed. And somewhere, in the background of every design review and certification audit, the recorder waits as a silent reminder of what happens when confidence exceeds understanding. Because no matter how advanced the machine becomes, it will always be subject to the same forces: stress, fatigue, heat, and time. Those forces are patient. And when they prevail, the black box will once again fulfill its final obligation, not to save the aircraft, but to ensure that its failure is not meaningless. The investigation does not end when the probable cause is written. In aviation, a conclusion is never a full stop. It is a comma. Once the data has been decoded, once the timeline has been reconstructed and the chain of failure mapped in forensic detail, the industry turns inward. Design offices reopen assumptions that were once considered settled. Certification authorities revisit regulations written decades earlier, often in response to different technologies, different materials, different operational realities. The black box does not merely explain a single accident. It challenges the future. This is where the true legacy of the recorder emerges. Every recovered dataset feeds an expanding body of knowledge about how complex machines actually behave outside the laboratory. Wind tunnel models give way to real-world stress histories. Finite element simulations are confronted with recorded loads that exceed predictions. Human-machine interfaces are evaluated not in idealized scenarios, but in moments of cognitive collapse. The recorder transforms isolated tragedy into collective learning. One of the most profound shifts driven by recorder data was the evolution of fatigue certification philosophy. Early aircraft were certified against static strength requirements, with limited understanding of long-term cyclic damage. Recorder timelines, combined with wreckage analysis, demonstrated that failure was rarely the result of a single overload. It was the culmination of millions of cycles operating well within safe limits. This forced regulators to mandate full-scale fatigue testing. Entire fuselages were pressurized and depressurized repeatedly until they tore apart in controlled environments. Crack interaction effects, multiple small cracks linking into catastrophic failure, were observed directly for the first time. These phenomena were not theoretical. They were documented realities revealed by accident data. The black box made denial impossible. Material science advanced in parallel. Aluminum alloys were reformulated for improved crack growth resistance. Composite structures were redesigned with fail-safe load paths and damage tolerance criteria tailored to delamination rather than fracture. Inspection technologies evolved, driven by the need to detect damage earlier than ever before. Yet, even as structures improved, the recorder continued to expose another uncomfortable pattern: the limits of prediction. Aircraft systems became more reliable, but also more interdependent. Redundancy increased, but so did the risk of common mode failure. Software reduced pilot workload in nominal conditions, but amplified confusion when assumptions were violated. The recorder revealed that safety was no longer dominated by component strength alone. It was governed by system behavior over time. This insight reshaped engineering culture. Design reviews began to focus not only on what a system should do, but on what it would do when everything else went wrong. Failure modes and effects analyses expanded beyond hardware to include software logic and human response. Simulators were updated to reflect real accident sequences derived directly from recorder data, not hypothetical scenarios. The box, silent and passive, became a powerful voice in design debates. But with this influence came a paradox. As safety improved, accidents became rarer and more complex. When failures did occur, they often involved subtle interactions that were harder to detect, harder to interpret, and harder to accept. Public tolerance for uncertainty diminished. Expectations of perfection grew. The recorder was increasingly expected not just to explain accidents, but to justify the entire system. This expectation borders on hubris. The black box does not eliminate uncertainty. It manages it. It narrows the unknown after the fact. It does not, and cannot, make technology infallible. To believe otherwise is to repeat the very mindset that necessitated its creation. This is the final lesson embedded in its history. Every generation of engineers believes it has solved the problems of the past. Every generation introduces new wants. Materials change. Algorithms evolve. Interfaces adapt. But the fundamental truth remains unchanged. Complex systems fail in complex ways. The recorder exists because humility had to be engineered into aviation. It is a physical acknowledgement that no design is immune to error, no calculation immune to oversight, no system immune to time. Its layered construction mirrors this philosophy. Each shell, each buffer, each redundant path is an admission that single points of confidence are dangerous. Even its color tells a story. Not black, but orange, chosen not for symbolism, but for the simple, pragmatic reason of visibility amid destruction. There is no romance in its design, only intent. As the industry now looks toward autonomous flight, artificial intelligence, and increasingly opaque decision-making systems, the role of the recorder becomes even more critical. Future aircraft may make decisions faster than human cognition allows. When those decisions lead to unintended outcomes, understanding them will require records of internal logic, not just physical states. The black box will have to evolve again, not just to record actions, but to record reasoning. This introduces new challenges. How do you log decision pathways without overwhelming data capacity? How do you preserve interpretability when algorithms learn and adapt over time? How do you ensure that future investigators can understand systems built on models that did not exist when the aircraft was certified? These questions have no easy answers. What history suggests, however, is that answers will not come from confidence alone. They will come from failure, followed by recording, followed by analysis. The cycle will repeat, as it always has. The black box will remain at the center of that cycle, not as a symbol of failure, but as a safeguard against forgetting. Because without recorded truth, accidents become stories. Stories become myths, and myths breed complacency. The recorder interrupts that process. It replaces narrative with evidence. It forces uncomfortable clarity where speculation would otherwise thrive. In this way, the black box is not merely a tool of investigation. It is a moral instrument. It enforces accountability across time, across organizations, across generations of engineers who will never meet the victims whose data shaped their designs. Every rivet redesigned, every procedure updated, every warning clarified carries the fingerprint of past recorder data. The aircraft that depart runways today carry more than passengers and cargo. They carry the accumulated lessons of countless failures, distilled into metal, software, and training. And buried deep within their structure, they carry the device that ensures those lessons will continue to accumulate. Silent, indifferent, essential. The history of aviation is often told through milestones of success, speed records, altitude records, range records. But its true progress is written elsewhere, in wreckage fields, in laboratories, and in the memory chips of devices designed to survive the unsurvivable. Steel bends, aluminum cracks, composites delaminate. Algorithms misjudge. Humans misunderstand. The black box does not judge. It endures long enough to remember. And because it remembers, aviation moves forward, not blindly, but with the hard-earned knowledge of where confidence failed and physics prevailed. The history of aviation is written with steel, ingenuity, and the will to challenge limits. Welcome to the Vault.